Okay, good morning. The quiz. So we talked about that in recitation. The quiz had some aspects that were confusing. So here's what we're going to do about the quiz. If you're not happy with your quiz score, what you can do is submit a correction. What does that mean? That means turn it back in with a brief but meaningful analysis of what thinking about it now. So what you write could go something like this. When I was working this problem, I was thinking X, but now I realize that Y, and so I see that the answer should be this or that. Now, if what you're going to write is, when I worked this problem, I thought the answer was A, but now I see that the answer is B, don't bother. Okay, that's not what I'm looking for. So what I'm looking for is a thoughtful but brief analysis of what confused you or what error you made, and how you're thinking about it now. Does that make sense? Okay, turn that in a week if you want to. You can raise your quiz grade to a maximum of 8. Okay. So if you got a 9.5, don't bother. Yes, Robert. What?
Can I do that for last week's quiz?
No, that's this quiz. Okay, so we've been talking about energy, and I should add that this afternoon's recitation, I think we'll spend doing some practice problems related to chapters 4, 5, and 6. So if you have questions or things you'd like to work on, bring them along, and we'll work on it in recitation. So we've been talking about energy, and we've talked about energy of a single particle, which does not involve potential energy, and then we've talked about energy of multi-particle systems, which can contain interacting objects, and therefore there can be a potential energy term associated with the system. And we've talked about two kinds of potential energy. We've talked about gravitational potential energy, and we've talked about electric potential energy. And both of those kinds of energy we're basically treating the objects involved as if they were point particles. Okay, so they couldn't deform or get hot or have energy inside them. All they could have was rest energy, kinetic energy, and this energy due to the interaction. But in the real world, not everything's a point particle, right? And we saw in chapter 4 that in order to understand contact forces, so compression forces, tension forces, we had to think about the microscopic structure of objects that are made of lots of atoms bonded together by chemical bonds, which end up being very spring-like. And those things aren't point particles. They can deform, they can stretch, they can compress, they can get hot. And so we have to talk about, for a complete discussion of energy, we have to talk about energy inside these extended objects, kind of energy we'll call internal energy. And to talk about internal energy, we need to go back to our model of a solid as composed of atoms connected by covalent bonds, and we modeled a solid metal, which is a nice orderly solid, as a lattice of balls, which are the nuclei, the massive nuclei, and some inner electrons connected by spring-like connected by springs, which is a model between them. And so what we're going to do today is start thinking about the kind of energy there can be inside such an object. And up to now we've drawn these balls and springs as just being stationary, but they aren't. All the atoms inside the object are moving around, and not surprisingly, the amount of motion, and will be more quantitative, is related to the amount of energy inside the object. Now it seems clear there's kinetic energy. One component of this internal energy is kinetic energy, because these atoms are moving and they have masses, and so there's kinetic energy associated with the vibration of these atoms. But there are these spring-like bonds also, and they can be compressed and stretched, and so we need to worry about the energy that can be stored in springs. And so our goal today is to apply all the ideas we've developed in Chapter 6 to thinking about a potential energy associated with springs. And the ultimate goal is to relate it back to this model of solids, and to be able to talk about energy inside, internal energy inside a solid object associated with motion of the atoms and compression of the bonds, and then relate that to things we can measure like temperature or changes in temperature. So that's the goal of this chapter. And so we're going to start out today talking about the energy associated with mass spring systems. So let's go back to our discussion of about mass spring systems. You did some experiments with springs and masses in lab. So let's go back to thinking about a situation where we've got, let's make it a very simple situation. We have a mass connected to a spring sliding with very, very, very low friction on a horizontal surface. Okay? So here's our spring connected to some kind of a wall. Here's our mass. Here's a surface. The spring will oscillate back and forth that way. And there's some equilibrium length of the spring, L0. And what we're going to do is we're going to start it with an initial situation where we stretch the spring and let it go. So that's our initial stretch. And it's going to oscillate back and forth. So let's think about if we tried to graph, let's call this the x-axis. If we tried to graph, let me do this over here. Try to graph x versus t for this system. What's it going to look like? So here's t. This is x. So what would a graph of x versus t look like for this system? Well, it's not exactly going to be a sine because we're starting it with an initial stretch. So it's a cosine, isn't it? Right. So it's going to look like an initial stretch, and then it's going to be relaxed, and then it's going to be... Okay, and remember that we actually did an analytical solution for this system and discovered that indeed we could write an equation for x versus t that looked like a cosine of omega times t, where omega was 2 pi over the period of the oscillation. Okay, what does the graph of v sub x versus t look like? Okay, so, okay, negative sign, because when we start here, v is 0 at the butt, and it's going to head in the minus x direction, isn't it? Yep. So we're going to, so we want, see if I can get this right. Something like this. So something like that. Okay. So when the maximum stretch, the speed is 0. At the equilibrium position, speed seems to be a maximum. Well, magnitude of the speed. What does a graph of kinetic energy versus time look like? Really? It's the same thing? Okay, kinetic energy is going to be, so what's the approximate expression for kinetic energy of something that's moving slowly? Half mv squared. So is it going to be a sine wave? Can't be negative, can it? No. Okay, so it's 0 when v is 0. It's going to have a maximum when the speed is highest, right? And so it's going to be 0 here, and then a max again, and this is consistent with the fact that the direction of motion doesn't make any difference when you're talking about energy, right? It's just speed. Okay, so it's going to look something like that. That seem right? So it looks like as this mass oscillates back and forth on the spring, the kinetic energy of the system is changing. Now the energy principle still applies. So we have change in kinetic energy, or rather change in energy of the system is work done by the surroundings. So system here, what in the surroundings can be doing work on this system? The system being the mass plus the spring. So the system Okay, well, the Earth is exerting a force down, right? But since the momentum's not changing in the y direction, we conclude that the force, upward force by the surface, is equal and opposite to, we'll call it the normal force here. Now, there would be a friction force in a real system, but on our idealized system, we've said that it's very, 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 very small. So that's, right? So what about so what else is there that could do work on this system? Well, we said friction, friction is negligible, right? So our system is gonna oscillate forever. Maybe we've suspended it on a bed of air. So we have an air table here, like an air hockey table, and the spring is a very ideal spring that isn't really getting hot or deforming or anything. So it is connected to this wall, though. Right? That's not part of our system. So does the wall do work on the system? So work is delta x in this case, right? So it's exerting a force on the system. Okay, talk to your neighbor for a minute. Is the wall exerting a force on the system? I'm seeing yeses and no's. Okay, so the wall is exerting a force on the system, right? If we pull this thing back, why aren't we just walking away with it? Well, it's attached to the wall, and the wall is exerting a force. And does the direction of the force by the wall? Okay, so we pull this way, the wall is definitely pulling that way, right? What if the spring is compressed? Yeah, then this force suddenly has to go. Okay, so the wall's doing fairly active thing. So the wall is definitely exerting a force. How much work is that force doing? So work is the product of the force applied times the distance through which that force acts. So we're applying a force, the wall is applying a force to that atom right there. How far does that atom move? Yeah, the atom that's attached to the wall doesn't move. And so therefore, delta x is 0, and the work done by the wall is 0. That makes sense. Is energy flowing from the wall into the mass spring system? No. No. So the wall is actually doing 0 work in this case. Is the wall affecting the momentum of the system? Absolutely, because the force acts through various time intervals delta t, and therefore it's going to change the momentum of the system. But the force, the point of application of the force, the atoms in the spring that are attached to the wall don't move. And therefore the wall is doing no work on the system. The wall is not putting energy into the system. So it looks like in our energy equation, the work done by the surroundings has to be 0. Now we know that the kinetic energy of the system is changing. We just graphed it. But it looks like the total energy of the system has to be constant. So what has to be true of the potential energy associated with this mass spring system? What is it going to look like if so this is K. So what would the potential energy look like? Yeah, it's gotta add up to a constant, right? K plus U has to add up to a constant. So we want K plus U to add up to a constant, which means that when the kinetic energy is 0 and the system is at rest, the potential energy must be at its maximum, and that has maximum extensions of the spring, so that makes some sense. And when the kinetic energy is maximum, the potential energy better be 0, so we're going to get some sort of a potential energy curve that looks like that, presumably. Yes?
Why is potential energy positive in this case?
Why is potential energy positive in this case? That is a very good question, and we will come back to it. It's very odd to have a positive potential energy, isn't it? So that's an excellent question, and it's one of the things we'll come back to. U has to look something like that in order to make the energy principle actually work out. So let's see if we can figure out what this potential energy function for a spring, this very idealized spring, should look like. So remember that we had we came up with this equation simply actually from the work relationship. We said remember the change, we defined the change in potential energy as the negative of the work done by internal forces, so that was minus Fx delta x internal. And so rearranging slightly, we got a du dx was minus Fx. Okay, so so our job is to do that here to see if we can get a function. So the spring force, the x component here, and again we're going to take x such x is 0 when the spring is at its equilibrium length. So x basically is the stretch in this case. We've set our coordinates so that x is 0 when the spring is relaxed. So we have a minus k sub s x in the direction 1, 0, 0, okay, is du dx. So basically modulo a constant, that's a minus. So basically we have modulo this constant, the derivative of some function gives us x. So taking an antiderivative, what's a good function? Yeah. So So we get U is equal to a half k sub s x squared. And let's just check by differentiating du dx. We'd get a 2 here. That would, okay. So it looks like the spring potential energy is going to be now really x isn't a particularly meaningful coordinate here. It could be y or it could be z. So we can actually, since what we did is take x equals 0 there, we can actually write it as a half k sub s s squared. So for the potential energy of a spring. Now that's a pretty odd looking potential energy function. So if we have energy versus stretch, it's going to be 0 here. Looks like a parabola, doesn't it? Yep. So we've got now that's very weird indeed, because it's greater than 0. It doesn't go to 0 at large distances. All the states are bound states, but k plus u is greater than 0. So this is really strange. And this is basically a potential energy function for a very idealized spring. Now, how to make it look more like a potential energy that actually makes sense? Well, there could have been a constant in here. So we could have an additive constant that's just that's some negative number, which would mean that our potential energy function would look like that instead, where this is this negative E0. That's a little bit helpful because at least it's in fact, just to be clear, let's make it a minus, just to make it clear that we're and now let's think about a real spring. So this ideal spring looks like you can just stretch it infinitely long, because this function just goes on forever, right? Well, a real spring, you can't do that, right? I mean, you pull enough and sooner or later all the coils will straighten out and then you've got a straight wire. And that's going to have a different stiffness, but if you pull on that for a while, it's eventually going to break. So it might make more sense to say that as we stretch this spring, we get to a point where it gets much stiffer, and then eventually it just breaks. What about in the other direction? We push a spring together and eventually the coils hit each other, a real spring. So you can't compress it infinitely. Here it looks like we could just keep compressing and compressing and compressing, and the spring would get arbitrarily, microscopically short, but that's not true with real atoms. So, in fact, when we start getting the coils hitting together, or in our ball spring model of a solid, when the atoms start getting too close to each other, the repulsion is going to get much greater. So it looks like we'd actually get something that looked more like that. So our potential energy graph for a real spring would be more like this, where we have this parabolic region here, but as we get farther and farther away from some sensible spring behavior, it doesn't do that anymore. And in fact, the equation for potential energy of two atoms together looks a little bit like that. It's called the Morse potential energy. And it looks like something like this. It looks like 1 minus, there's actually e to the minus alpha times r minus the equilibrium location minus, so we end up, ends up looking parabolic at small extensions, but we'll consider this as an equation that actually approximates the behavior of a real spring or a real chemical bond in a bonded system. And if we, let's see here, here we go. So if we use that equation, so here's our horizontal mass spring. If we add graphs of kinetic, and this is using the algorithm you know and love, where you calculate the force on the mass, apply that force for a time delta t to get a change in the momentum of the mass, and the force is calculated by being the stretch of the spring. Use that momentum to get an approximation for the average velocity. Use that average velocity to update position. Now the stretch is different. Do it again. So this is a computation just like the ones you've done. So here's our system, and let me make this a little smaller. I'd like to get a graph onto the same. Move. There we go. So here we go. So we're graphing kinetic energy, potential energy, the sum of k plus u. What's the green arrow? Could be momentum. It's in this case v sub x, but same. Okay. So which line is, we started it by stretching it. So which line was kinetic energy? Red. And the blue line must be the spring potential energy. And the purple line is K plus U. And it's positive because we didn't subtract a constant value here. But the bookkeeping works out right. Okay? Yes?
I kind of lost where the negative E naught came from. I lost it. Where did the negative E naught come from? I kind of lost it.
Oh, well, the question is, where did this negative constant come from? When we solve this equation, we'll write it with S. We solve this equation by taking an antiderivative. We said that if we differentiated 1/2 k sub s squared, we got k sub s times s. But suppose we differentiated this expression with respect to s. We'd get the same answer, right? So there could be a constant in here that there could be some arbitrary constant in that expression. And we decided we wanted a negative constant because we wanted the potential energy to make physical sense in a system that wasn't necessarily an ideal system. So if we're talking about ideal springs, as we were here, we'll ignore that constant. But if we're going to talk about a real spring, we're going to talk about two atoms bonded together by a covalent bond, then we want to have some bound states where k plus u is actually less than 0. And so we're going to remember that there's this negative we could add in. Other questions about this? All right, well, let's see if we can do something with this. Like we've been doing before. Let's see. Yeah. Okay, so we ought to be able, now that we have a new expression for potential energy for a mass spring system, we ought to be able to use it to solve for various things in exactly the same way we've been doing all along, using all the same ideas we've developed in Chapter 6. So let's see if we can solve a problem. So we have one of these horizontal mass spring systems. The stiffness of the spring is meter. The relaxed length is 0.25 meters. We have a 50-gram mass attached. You stretch it to 0.29 meters. You release it from rest. Moves with negligible friction. How fast is the mass going when it gets back to its equilibrium length? So how do we think for a minute about how we'd go about, make a plan. Let's make a plan to solve this problem, okay? Okay, so is there a fundamental principle we can use to solve this problem? The energy principle! What a great idea! So, we have the final is the initial plus work done by the surroundings. And in this case, the work done by the surroundings is 0. So what are the energy terms that go on each side? So what should I be writing here? The system is, what are we going to pick as the system? Mass plus the spring. What are we going to pick as the initial state? Okay, so stretched. And we're releasing it from rest, right? And the final state is going to be stretch is 0, V is not 0. Okay. So in the initial state, we've got kinetic energy of the system plus spring potential energy, right? And in the final state, we have kinetic energy plus spring potential energy. Now, which of these things is 0 where? Initial kinetic energy 0. And is anything 0 here? The final potential energy is 0, isn't it? Because if the stretch is 0, then s squared is 0. So that's a 0. What? What about the negative constant? Well, we have, so let's write it out. We have k final plus a half k sub s, s final 1/2 m v final squared, 1/2 m v initial squared plus 1/2 k sub s times 0 squared minus b0. This is why we often just don't bother with it when we're doing these spring problems, because this constant would show up on both sides and so cancel out. But it's a good question. Okay, so this was 0 and that was 0, and that exists on both sides, so we have 1/2 mv final squared equals 1/2 k sub s s initial squared
Initial s wasn't 0.
Ah, initial s is not 0. And so v final squared is going to be, we have a couple 1/2s we don't need, k sub s over m times, what was the initial stretch? So it was 0.04 meters. And we might as well put in all these numbers. So k sub s was 3 newtons per meter and 0.05 kilograms. And we come out, yes? No? Yes? So did anybody actually get a number? You didn't work? I think it's 2.7.
That's just my go-to answer, it's just 2.
2.7 is the thing you'd always guess. Okay, so we did exactly what we've been doing, right? Nothing up either sleeve. Just apply the energy principle. Make sure you're counting all the right energy terms. Okay. Let's consider a different system. So we have a vertical spring that's just standing on the table. It's attached to the table, so it doesn't fly off. We drop a block onto the spring, and the goal is to find the speed of the block when it's 0.3 meters above the table, and the relaxed length of the spring seems to be 0.4 meters, so that suggests that the block has compressed the spring a little bit. Okay, so take just a minute and think about a plan for this problem. Okay, what's... Yes?
Is an arrow pointing down with 2 meters per second there? Does that mean that it starts with 2 meters per second?
Yes, what we know is that when the block is 0.8 meters above the ground, it's traveling downward with a speed of 2 meters per second. So that's what we know. So, the energy principle.
Shocker.
Now in this case, what are we going to choose as our system? The block, the spring, that's it? The earth. We can put the earth in the system. Let's put the earth in the system. That makes it simple because the surroundings, as long as we neglect air resistance, the surroundings aren't going to do any work. What's our initial state? It's speed is 2 meters per second. Y is 0.8 meters. Stretch of the spring is 0. And the final state okay, we don't know the speed. That's what we're we know that the block is 0.3 meters, and the stretch we can is 0.3 meters minus 0.4 meters, I guess. Okay, so what terms go in our energy equation here? So let's try to center this. So that's 0. So when initial energy, we have initial kinetic energy plus what kinds of potential energy terms? So the initial gravitational potential energy and the initial spring potential energy, presumably. And on the final side, we've got the same thing. And which of these terms are 0? So this is 0 initially. And is anything 0? Not necessarily, unless the block has come to a stop, which we don't know, right? Okay, so we have 1/2 mv final squared plus, are we going to use minus gmm over r here? It's going to be really tough to calculate gravitational potential energy if we do that, because the distance from the center of the Earth isn't changing very much. So we're going to use this approximate thing where, so we can say it's mg times y final. Remember that the change in gravitational potential energy near the Earth's surface UG, delta UG was just mg delta y. And this can be positive or negative, which some of you didn't think entirely clearly about on the quiz. And UG really is going to be mgy plus a minus g mass of the Earth, mass of the object over the radius of the Earth, right? So we've got this big additive constant here for the potential energy at the surface. But just like this E0 thing, it's going to be on both sides of our equation. So we can actually just kind of leave it out and write it this way. And so we have a half k sub s. S final squared is a half mvi squared plus mgy initial plus 0. Now if we care, we can simplify our calculations by canceling the m, which actually does drop out. So what's our unknown again? Okay, so here's our unknown. Do we know the final y position? Yep. We know the final stretch? Yep. We know the initial speed. Suppose that I gave you, so questions about this. Okay. So suppose we phrased the problem differently. Suppose we said, find the maximum height to which the block is going to rebound. So you drop the block, compresses the spring, gets shot back up in the air. How high is it going to go? So what would you take as what would you take as the initial and final states here?
Final velocity would be 0.
Final velocity is indeed 0. So we're going to take as a final state speed is 0 and y is y max. So we're definitely going to take as the final state v equals 0. What's a possible initial state? Well, could we take this state, the one where the spring's compressed to, the block's sitting on the spring and it's compressed to 0.3 meters long. We know everything about that state, right? So we could use that state. Can we use this state?
That could be initial.
Can we use this state as an initial state? So neither of these, if we pick this as an initial state, is it going to work? Neither of these states has any information about the spring, right? Is that okay? Well, does the spring put energy into the system? So this is a completely legal initial state to choose. Okay, and if we do it this way, V equals 2 meters per second, Y equals 0.8 meters, we'd get now if we choose our system, let's assume we've taken the same choice of system, so we're still using the block, the spring is the earth. What are the terms that show up in our energy equation here? So we have K final plus UG final plus US final is K initial plus UG initial plus US initial. Spring energy is 0 in both cases, right? But that's fine. Gravitational potential energy has increased or decreased as we separate the objects? increased, so the kinetic energy decreased. That makes sense. So, and as you pointed out, final kinetic energy is 0. So that leaves the final gravitational potential energy is equal to the kinetic energy of the initial kinetic energy plus the initial gravitational energy here. The spring didn't put any energy into the system. It temporarily stored some energy, and then it released it back into the system. So energy flowed from kinetic to spring potential energy, back to kinetic, and there's some gravitational potential energy changes. So that's a completely legitimate, and it's almost like sort of going backwards in time. If I had just said, never mind the spring, if I'd said, well, here's this block and it's falling at this speed, how high was it when you dropped it? You would have solved that problem, right? Could we have picked a different, what would have happened if we'd picked this compressed situation here? And that would have been okay too, right? In that case, we would have had a non-zero spring energy here, but the gravitational potential energy term would have been proportionately lower, and that would have worked out too. So either choice of initial and final states is legitimate, and in this case, we'll give you what you want. I mean, there are many cases where you can choose initial and final states where one of them doesn't contain the unknown you want, or you don't know enough things, and then it's just not productive. It's still legitimate, but it's not productive. But in this case, it would have been fine. Questions about that? All right, we don't have time to do another big problems, so we'll save it for this afternoon. Questions about this? So, are you clear on on what to do about the quiz? If you want to improve your score, you write a very brief but very clear statement with physics content about what confused you or what you were thinking at the time and how you're thinking about it now. Turn it back in. You can get your score raised up to a maximum of 8. Okay? Yes?
What's the Morse? So are we just like disregarding the Morse potential energy formula for like the sake of this class, or?
I don't think we're ever going to do a calculation using the Morse potential energy, but we will actually refer to the form of the curve. This potential energy curve where we have a potential energy curve that looks something like that really does describe the potential energy of the interaction between two atoms bound by a covalent bond. And this bottom of the well is in fact a parabola. And we'll see that this is important when we talk about things like the vibration of two atoms bonded together. Okay, we're going to end up using this piece of that potential energy curve. Okay? Other questions? Okay, yes?
Are you going to be posting a test review?
No, what you should do, I'm not going to post a test review. What you should do is redo homework problems and do odd-numbered problems that you didn't do, whose answers are in the book. Okay?
It's essentially 4 through 6.
It's 4 through 6. I mean, it's 4 through 6 except that it's 1 through 6 because you need 1 through 3 to do 4 through 6. So, but emphasis on 4 through 6.